In this lesson, we'll continue practicing our integration technique of substitution, but we'll do so with integrals of a type that we have not seen before, and they're called indefinite integrals. So if you were to compare the learning target for today with the learning target from last lesson, you'll notice two differences. We were practicing substitution with definite integrals last time, and when we did that substitution, we had to change the variables and limits. You'll notice that limits are not mentioned in this learning target because indefinite integrals actually do not have limits. So let's start by defining what an indefinite integral is. So we already noticed that an indefinite integral has no limits, but what we need to know is that it produces not just a specific antiderivative, but a general set of functions that are all antiderivatives of f of x. And let's talk about why using this pretty basic example. If I asked you what the antiderivative of 2x is, you'd most likely tell me it's x squared, which is true, and we can check that by taking the derivative of x squared, which is 2x. But what we haven't thought of yet is that if x squared had a constant added or subtracted to it, it would also have the same derivative of 2x, and therefore x squared plus 1 could be an antiderivative of 2x. To further demonstrate what we need to think about is, if I added a different constant like 12, it would have the same antiderivative, and so on. So hopefully you can see that there would be an infinite number of antiderivatives of 2x, and that's why we say it produces a general set of functions. So we can't just say there's an infinite number of constants here. Mathematicians had to come up with a way to acknowledge and also quantify that unknown constant. So they came up with the capital C that will add to the antiderivative every time we take an antiderivative of an indefinite integral. So before we start talking about substitution with indefinite integrals, I wanted to try several examples when we're just getting used to that new unknown constant C. So we're just going to be practicing some basic antiderivatives and remembering to add our unknown constant plus C. So you can think of it as doing the plus C instead of evaluating the limits for the definite integral. So it's not an extra step, it's just a step instead of evaluating. Looking at the first example, we've got the integral of 8x cubed minus 1, and I just want to clear up a misconception that I've seen with several students. When they see these parentheses, they think that's an indicator of needing to use substitution or maybe even power rule, thinking there's a first power outside of those parentheses. And while that is true that there's a first power, when there's no power other than 1, these terms are just going to be treated separately when we find the antiderivatives. So the antiderivative of 8x cubed using the power rule, we'd add 1 to the power, so it'd be 8x to the 4th over 4, so that would give us 2x to the 4th. The antiderivative of minus 1 would be minus x. And at this point, we would have drawn brackets for the definite integral and evaluated our limits, but instead, for the indefinite integral, since there's no evaluation to be done, we just have to remember the unknown constant plus c. The second example is probably the trickiest of our trig functions because we can never really decide if it should be positive or negative. So if I were to guess that it was cosine of x, I would do a quick mental check. The derivative of cosine is actually negative sine. So you should be able to figure out by checking your derivative that it should actually be negative. And with no limits to plug in, I remember my unknown constant plus c, and I'm done. I'd like you to try the rest of the examples on your own and check your solutions using the posted solution key for the notes, and we'll also talk about these examples in class as well. I think we're now ready to move on and look at indefinite integrals using substitution. If you skim the list of steps, you'll notice that the first 3 are identical to the first 3 steps of substitution with definite integrals. So we start by setting up and doing the substitution the same way. We'll talk about how steps 4 and 5 are a little different when we get there. So using this first example, right away I see a trig function, so it's good advice to use those parentheses in your trig function to help you identify that inside function. And that is going to be our u function. So we've got x cubed, and du will be 3x squared dx. With our first step done, I went ahead and decided to rearrange the terms in my integral so that they're better set up to match my u and du. So I moved the x squared back with the dx, and I left a space because I noticed that we need a constant 3 inserted into the integral. And we learned in our last lesson that to make that legal, we actually have to insert a 3 over 3. Now that our constant is in place, let's go ahead and move on to step 3, which is to substitute the u and du terms. So when I rewrite the integral, I keep the cosine, I substitute u for that x cubed, and the entire expression 3x squared dx gets replaced by du. So you might remember this constant, the one that we needed to make it legal, is kind of in the integral that we don't need anymore, so we'll use that property and put it to the front, keeping in mind that this is actually a 3 in the denominator, so the constant that gets moved out front is a 1/3. If you look back at your notes for substitution for definite integrals, step 4 would say antiderivative and evaluate. This one says we still have to find our antiderivative, but then to remember our plus c, and I put that in bold and I will underline it too, because that's easy to forget when you're thinking so hard about your antiderivative. So the antiderivative of cosine should just be positive sine of u and then plus c. And our fifth and final step is to resubstitute the x function for u. And the reason we do that is because the question was asked in terms of x, and so that the answer we give should be in terms of x as well. So I've got 1/3 sine, and then I'm going to resubstitute instead of u. Originally I had x cubed defined as u. So the sine of x cubed plus c is my final answer. So now that you've seen one example using all the steps, we'll save the rest of the examples to do together in class.